Dear friends, Maths Aspirants is a community of students, research scholars, and teachers who loves mathematics. Initiated by myself in 2017, and we used to arrange online problem solving sessions and test series to help the students who prepare for different national level competitive examinations like JAM, NET, GATE, etc. As a part of that series, today we have Miss Binny Sharma is with us. Miss Binny is currently pursuing PhD at Maharshi Dayanand University, Rohtak, Haryana. She did integrated M.Sc in mathematics from MDU, and she cleared CSIR NET with JRF and GATE. I would like to express my sincere gratitude and thanks to Ms. Binny for accepting our invitation and joining with us. I welcome everyone to this program. Welcome, Binny.
Thank you, sir, for inviting me, and I also welcome you all. And it's a great pleasure if I am deliver this lecture. So today we will be discussing about the eigenvalues and the eigenvector. It is the one of the most important topics. In each exam, you get two or more questions, minimum two or more questions. So it is very important concept. So today's topic is eigenvalues and eigenvector. The first is eigenvalues and eigenvector of a linear operator. So let T be a linear operator on a vector space VF. If there exists a non-zero vector V belongs to V such that TV equals to lambda V. So TV equals to lambda V for some lambda belongs to F. Then V is called an eigenvector of T corresponding to lambda, and lambda is called eigenvalue of T corresponding to V. If we say lambda is an eigenvalue of T, then we can define that a scalar lambda is said to be an eigenvalue of T if there exists a non-zero vector. We have to show there is a non-zero vector belongs to V such that TV equals to lambda V. Okay. Eigenvector also known as the characteristic vector, and eigenvalue is also called as characteristic value or root. So this is the definition of eigenvalues and eigenvector of a linear operator. But if we want to define eigenvalues and eigenvector of a matrix, say let A be a square matrix of order n. A matrix should be square. Okay. Over a field F, if there exists a non-zero column vector x belongs to Fn such that Ax equals to lambda x for some lambda belongs to field F, then x is called an eigenvector of A corresponding to the lambda, and lambda is called an eigenvalue of A corresponding to the x. X is eigenvector. We have an example. Let A matrix. Now we have to find which one of the following are the eigenvector. So first V1 should be non-zero, and here V1 is non-zero. Second condition we have to check A V1 equals to lambda V1. So just multiply the matrix and V1. What we got? -2, -2, 0. And we take -2 as common and we get 1, 1, 0. It's itself a V1 vector. So what we get? A V1 equals to -2 V1. So here lambda equals to eigenvalue is -2. And we can say that V1 is an eigenvector corresponding to the eigenvalue -2. Similarly, we can check whether V2 is eigenvector or not. When we solve A V2, we get 4 times V2, 1, 1, 2. So here again 4 is an eigenvalue corresponding to the eigenvector V2, and V2 is an eigenvector corresponding to the eigenvalue 4. V3, that is 2, 1, 1. But here what we find 2, 4, 10. We cannot find a common value. So here V3 is not an eigenvector of A for any V belongs to C or any lambda. Now the question arises, if whether sum of two eigenvector of a matrix is again an eigenvector. From the above example, V1, V2 are the eigenvector of a matrix A. But when we add V1 plus V2, is not an eigenvector of A. Just multiply matrix A and V1 plus V2. V1 is 1, 1, 0. The V1 plus V2 equals to 2, 2 and 2. We just multiply A and V1 plus V2. But what we get? 2, 2, 8. That is not equal to lambda into V1 plus V2. So it is not necessary if two eigenvectors, sum of two eigenvector of a matrix is again an eigenvector. It's just how to find whether a vector is an eigenvector or not. First we have to find vector should be non-zero and it must satisfy the condition A equals to lambda V1. Okay. The next part is evaluation of eigenvalues and eigenvectors. How to find eigenvalues and eigenvectors? The first one, if let T be a linear transformation, then lambda belongs to field F is an eigenvalue of T if and only if T minus lambda is a singular. Here singular means if we have a non-zero vector V whose image is 0. It maps to the 0. But we have to clear V should be non-zero. The second result is let A be n cross n matrix over a field F, then lambda belongs to F is an eigenvalue of A if and only if A minus lambda is singular. In case of matrix, how we define the A minus lambda is singular? It means its determinant should be 0. Determinant of A minus lambda I should be 0. Now definition of the characteristic polynomial. Let A be n cross n matrix over a field F. The function f lambda, that is determinant of A minus lambda I, is a polynomial in lambda of degree n. This polynomial is called as the characteristic polynomial. And if we want to the characteristic equation, then we put this characteristic polynomial, this determinant equals to 0. Okay, so the characteristic equation of a matrix A is given by determinant of A minus lambda I equals to 0 or determinant of lambda I minus A equals to 0. Here the degree of the characteristic equation equal to the order of the matrix. When we solve the characteristic equation and we find we will get roots of characteristic equation, and these roots are known as the eigenvalues of that matrix. So if we want to find the eigenvalues, we have to solve the characteristic equations. The fourth result is let T be a linear operator on a finite dimensional vector space VF. If A is the matrix of T with respect to any ordered basis B, then scalar lambda belongs to F is an eigenvalue of T if and only if lambda is an eigenvalue of A. It means, let me show you example. Say we have an linear transformation. Okay, and we have to find the eigenvalues of this linear transformation. So what we do, we made a matrix A of T in standard basis. How to make matrix in standard basis? T of 1 0 equals to 1 comma 3. Similarly, T of 0 1 equals to 2 comma 2. Now we have to made 1 3 in the linear combination of 1 0 and 0 1, and we take transpose. You must be know how to make this matrix A of T in standard basis. So in that result, what he says, if we want to find the eigenvalues of T, then we make a matrix matrix with respect to any standard basis, and we will find the eigenvalues of that matrix. So the matrix or the eigenvalues of matrix and the eigenvalues of linear operators are same. The result 5, corresponding to a characteristic vector of a linear operator, there exists one and only one characteristic value. It means a v equals to lambda v. There may be a more than one vectors v1 v2, but there's only one eigenvalue. Okay, corresponding to the characteristic vector of a linear operator, there exists one and only one characteristic value. Next result says, corresponding to characteristic root of a linear operator, there exists more than one characteristic vectors. In fact, every non-zero scalar multiple of a characteristic vector is also a characteristic vector. The 7th result is, all eigenvectors together with zero vector form a subspace of V called eigenspace. We do not consider zero vector as an eigenvector because from starting we assume eigenvector should be non-zero. But if we consider zero vector with all eigenvectors, then it makes a subspace that is known as the eigenspace. How we define eigenspace? Let lambda be an eigenvalue of a linear operator T, then eigenspace with respect to lambda is known as the collection of the all eigenvectors who satisfy the equation TV equals to lambda V. Now the algebraic multiplicity. Algebraic multiplicity, it means how many times a root appears. Algebraic multiplicity of eigenvalue is the number of times it appears as the root of the characteristic equations. Let lambda square minus में 2 lambda plus 4 equals to 0. So algebraic multiplicity of 2 is 2. How many times a root appears? It is known as the algebraic multiplicity. Geometric multiplicity of an eigenvalue is defined to be the dimension of its eigenspace. It means number of elements in its basis. It is one of the most important result. GM lies between 1 is less than equal to GM less than equal to AM for each eigenvalue. If AM of algebraic multiplicity of an eigenvalue is 1, then geometric multiplicity is also 1. If algebraic multiplicity is 2, then geometric multiplicity is either 1 or 2. It may be a 1 or it may be a 2. The result 9 is a particular results. How we define the characteristic equation? Determinant of A minus lambda I equals to 0. But there is a formulas for 2 cross 2 matrix and 3 cross 3 matrix. That is, if we want to find the characteristic equation of a 2 cross 2 matrix, then we just apply this formula, lambda square minus में trace of A, lambda plus में determinant of A equals to 0. Similarly, for a 3 cross 3 matrix, the characteristic equation is lambda cube minus में trace of A, lambda square plus A11 plus A22 plus A33. These are the cofactors. Cofactors are principal elements. Okay. Minus में determinant of A equals to 0. Now we apply all those results in this example. So you must get an idea how to find the eigenvalues and basis of each eigenspace of the linear operator. Okay. So this is an example. We have given a linear operator T, which is defined as Txy equals to x plus 2y, comma 3x plus 2y. So I already told you how to make a matrix from a linear operator T in the standard basis. Okay. So we have made the matrix A, that is 1, 2 and 3, 2. Characteristic equation of A is given by A minus में lambda I determinant equals to 0. तो 1 minus में lambda, 2, 3, 2 minus lambda, determinant of this equals to 0. If we have a matrix A, B, C, D, its determinant is AD minus में BC. So we have applied the determinant 1 minus lambda into 2 minus lambda minus में 6 equals to 0. And what we get? Lambda equals to minus 1 and 4. I have just told you for a 2 cross 2 matrix, we have just simply apply this equation, lambda square minus में trace. Trace means sum of diagonal elements. 1 plus 2, that is 3. Some of these elements are known as the trace. So we applied lambda square minus में 3 lambda and plus में determinant of A equals to 0. So we can apply this formula. This is the general and this is the particular for 2 cross 2 matrix. The eigenvalue, what we got eigenvalues, lambda equals to minus 1 and 4. Now we are interested in finding the basis of each eigenspace. Eigenspace must satisfy the equation Ax equals to lambda x, because we have to find the eigenvectors, or we can say non-zero column vector, which satisfy the Ax is equal to lambda x. Then we what we get, A minus में lambda I into x equals to 0. This is the homogeneous system. Okay, you must have studied how to find how to solve the homogeneous system. So from the 1, 2, 3, 2, we have a matrix 1, 3, 1, 2, 3, 2. So we have just applied this A minus lambda I. 1 minus lambda, 2, 3, 2 minus में lambda, xy equals to 0, 0. We have two eigenvalues. One is -1, another is 4. So in first case, we have put lambda equals to -1. What we get? 1 plus 1, 2, 2, 3, 2 minus of -1, that is 3. Its rank is 1. You must know about the how to find the dimension of homogeneous system, that is n minus r. So 2 minus 1 equals to 1. That's why what we get, a plus b equals to 0, a equals to minus b, and we get an eigenvector 1 and -1. I've already show you a result corresponding to a eigenvector. There must be 2 or more eigenvectors. It would be an eigenvector. It means all non-zero scalar multiple of an eigenvector is also an eigenvector. Similarly, when we put lambda equals to 4, what if we get 1 minus 4, that is -3, 2, 3, 2 minus 4, that is -2. Its rank is 1. And how to find dimension? N minus r. It also 2 minus 1 equals to 1. Okay. In the same way, we find the eigenvector x2, that is 2, 3, corresponding to the eigenvalue 4. Now you must have an idea how to find the eigenvalues and the eigenvectors. It is one of the most important result. Let T be a linear operator on a finite dimensional vector space V, and let lambda 1, lambda 2, lambda n be distinct eigenvalues of T, and V1, V2, Vn be their corresponding eigenvectors. Then V1, V2, Vn are linearly independent. In above example, we have two eigenvalues and those are different. So their corresponding eigenvectors should be linearly independent. Result 11. Let lambda be an eigenvalue of an n cross n matrix A, then geometric multiplicity of lambda, that is dimension of eigenspace corresponding to the eigenvalue lambda, that is dimension of E lambda, and it is defined as dimension V AV equals to lambda V, and it is transformed into the dimension of the homogeneous system A minus lambda I V equals to 0. And how do we define dimension of homogeneous system? It is equals to dimension of nullity of A minus में lambda I, and nullity is defined as n minus r. Then n minus rank of A minus में lambda I. So in this way we can define geometric multiplicity of an eigenvalue lambda. The next question is, find all the eigenvalues, construct their AMGM table and find the basis for each eigenspace. We have a matrix A which is defined as 1, 1, -1, 1. characteristic equation is given as lambda square minus में 2 lambda, that is a trace, plus determinant lambda square minus 2 lambda plus 2 equals to 0. Here is trace and here is determinant. After solving this characteristic equation, we get lambda equals to 1 plus minus iota. So we have two eigenvalues, 1 plus iota and 1 minus iota. Algebraic multiplicity is how many times a root appear. So both have algebraic multiplicity of 1. And we have studied GM lies between 1 and algebraic multiplicity. So if algebraic multiplicity is 1, then GM should also be 1. So in this way, we construct a AMGM table. This table is important in to decide whether a matrix is diagonalizable or not. So you have to know how to make this AMGM table. Now basis of E 1 plus iota. Now we are interested in finding basis of eigenspace corresponding to eigenvalues 1 plus iota. So how we can 1 minus 1 plus iota 1, that is basically 1 minus lambda so 1 minus lambda minus 1 and 1 minus lambda. So here lambda is 1 plus iota, so 1 minus 1 of 1 plus iota 1 and minus 1 1 minus 1 plus iota. What we get? Minus iota 1, minus 1 and minus iota. Its rank is 1. So minus a iota plus b equals to 0. What we get this linear equation, and after solving this we get an eigenvector x1 1 and iota. Here there is only one free variable, and free variable decides dimension of homogeneous system. Okay. Similarly, lambda, when we have a lambda 1 minus iota, we solve the homogeneous system a minus lambda I x equals to 0. Here lambda is 1 minus iota and here also rank 1 and minus are also be a 1. So x2 is iota and 1. So what we get? Basis of E 1 plus iota 1 iota and basis of E 1 minus iota is iota comma 1. GM is dimension of eigenspace corresponding to lambda. So from this we can say geometric multiplicity of eigenvalue 1 plus iota is 1, and similarly geometric multiplicity of eigenvalue 1 minus iota is also 1. The second example is we have a linear operator T which is defined as Tx minus y plus z, comma 7x minus 5y plus z, comma 6x minus 6y plus 2z. Okay, So we made a matrix with respect to the standard basis. So what we get, A equals to 3 minus 1 1, 7 minus 5 1, 6 minus 6 2. And you can find characteristic equation by this equation, but there is a formula for 3 cross 3 matrix. So we have applied this formula, lambda cube minus trace, that is 3 plus 2 minus 5, that is 0, lambda square plus, and how to find cofactors, A11, that is minus 10 plus 6, that is minus 4. Here is A11 plus A22 plus A33. So A11 is minus 4. Now we have to find the cofactor of 2 element, that is determinant of 6 minus 6, that is 0. Similarly, we find the cofactor of A33, that is 3 into minus 5 minus 15 plus 7, that is minus 8. You must know how to find the cofactors. Plus determinant of A, that is 16. So what we get, the characteristic equation, lambda cube minus 12 lambda plus 16. After solving this cubic equation, we get values of lambda are 2, 2 and minus 4. Now the task is how to make AMGM table. So algebraic multiplicity of 2 is 2, and AM of minus 4 is 1. So we can directly say GM is also 1. But here's the confusion, whether GM of eigenvalue of 2 is 1 or 2. So so we need further investigation, how what is the geometric multiplicity of eigenvalue 2. So we take lambda equals to 2 and we solve the homogeneous system. I've already told you this many times, how to find A minus lambda I x equals to 0. We put lambda equals to 2 here and we get this matrix, that is 3 minus 2 1, that is 3 minus 2 is 1 minus 1 1, 7 minus 5 minus 2 is minus 7, and 1, 2 minus 2, 833 minus 2, that is 0. This is basically a homogeneous system. You must know how to make augmented matrix. So we have just applied the elementary row operations, that is R2 minus 7 R1 and R3 minus 6 R1, and we get this matrix. Okay. After applying all elementary operations, we get this matrix, and here rank of this matrix is 2, and nullity of this matrix is n minus rank A minus 2i is 3 minus 2, that is 1, and it decides geometric multiplicity of lambda 2 equals to 1. That's why we have written geometric multiplicity of eigenvalue 2 is 1 here. Basis of A2 is given by, just make A minus B plus C equals to 0 and minus 6C equals to 0. C is 0 and we get A equals to B. So we find out an eigenvector x1, that is 1, 1, 0. And this is the basis of E2. There is only one element in its basis because its GM is 1. Similarly, we can find basis of E minus 4, just minus minus 4 from the diagonal elements of a matrix A. Matrix A is 3 minus 1. So similarly, in the similar way, we have just make the augmented matrix and apply the elementary row operations, and we get this transform matrix. Here we get rank is 2 and nullity is 1, and GM, if nullity of this homogeneous system is 1, it means geometric multiplicity is 1. And by finding the values of making 7A minus B plus C equals to 0, 6B minus 6C equals to 0, that is B equals to C, and from here, if B equals to C equals to 0, B equals to C, then 7A equals to 0 and A equals to 0. So we can define basis of E minus 4 equals to 0, 1, 1. So in the first part, we have discussed how to check whether a eigenvector, how to check vector is a eigenvector or not. In the second part, we have defined how to find eigenvalues, eigenvectors, how to make AMGM table, and how to find the basis of an eigenvalue. Okay. Now the third part is diagonalization. It is very important, and in CSIR there must be a at least 2 or more questions. So diagonalization, the first definition is diagonalizable operator. A linear operator T on a finite dimensional vector space V is said to be diagonalizable if there exists an ordered basis B of V such that matrix of T with respect to B is a diagonal matrix. If we are able to find an ordered basis B such that if we will be make a matrix T with respect to basis B, then matrix will be a diagonal matrix. Then we can say that a linear operator is diagonalizable. The second definition is diagonalizable matrix. A n cross n matrix A is said to be diagonalizable if there exists a non-singular matrix P such that P inverse AP equals to D. And it is a similar condition for the similar matrix. It means if a matrix is a square matrix is said to be diagonalizable if it is similar to a diagonal matrix. If we want to check a matrix is diagonalizable or not, if that matrix is similar to a diagonal matrix, then we can say that matrix is diagonalizable, otherwise it is not. Now there are some results on diagonalizable. The first result says a matrix or linear operator is diagonalizable if and only if AM equals to GM for each eigenvalues. Now we know how to find the AMGM table. Just we have to check whether AM equal to GM for each eigenvalue. If it yes, so matrix is diagonalizable, otherwise it is not. It is very important result, so please keep it in mind. Result 2 says a matrix whose all eigenvalues are distinct is always diagonalizable. The reason is how if the all eigenvalues are distinct is always diagonalizable. If we have lambda 1, lambda 2, lambda 3, three distinct eigenvalues, and am or algebraic multiplicity of each eigenvalue will be 1. GM is also 1 if AM is 1. Then from the above result, we can say that matrix is diagonalizable. So a matrix whose all eigenvalues are distinct is always diagonalizable. Result 3. A n cross n matrix is diagonalizable if and only if it has n Li eigen vector. If we have n Li eigenvector of n cross n matrix, then matrix is diagonalizable. Result 4. A linear operator T on a finite dimensional vector space V F is diagonalizable if and only if there exists a basis of V in which all vectors are eigenvectors of T. If we are able to find a basis of V in which all vectors are eigenvector, then a linear operator will be diagonalizable. Result 5. Let A be n cross n diagonalizable matrix and x1, x2 and xn be n Li eigenvectors of A, and we make up matrix P by these eigenvectors if P equals to x1, x2, xn is n cross n matrix formed by taking x1, x2, xn as columns. Then P inverse AP is diagonal matrix in which elements on the diagonal matrix are eigenvalues of A. I'll show you how we will apply these results, so you have clear idea. The result 6. Every diagonal matrix is diagonalizable. If we have a matrix A and it is diagonal, then we can write here I inverse A I. We have found a non-singular matrix I which is similar to A. That is A is similar matrix. In definition of diagonalizable matrix, what we have find a n cross n matrix A is said to be diagonalized if there exists a non-singular matrix P such that P inverse AP equals to D, where D is a diagonal matrix. So in diagonal matrix, we have found a non-singular matrix I. So we can say every diagonal matrix is diagonalizable. Here A was diagonal matrix. So it satisfies the definition of diagonalizability. So every diagonal matrix is diagonalizable. Now we have an example. A 3 minus 2 2, 4 minus 4 6, 2 minus 3 5. We have to find whether it is diagonalizable or not. So characteristic equation of A is given by lambda cube minus में trace of A, that is 5 plus 3, 8 minus 4 minus 4 lambda square plus cofactors A1 plus A11 plus A22 plus A33 lambda minus में determinant of A. Then we get a characteristic equation lambda cube minus 4 lambda square plus 5 lambda minus 2 equals to 0. After solving this, we got lambda equals to 1, 1 and 2. So we will make an AMGM table. Here lambda 1 and its algebraic multiplicity is 2. And algebraic multiplicity of eigenvalue of 2 is 1. So directly we say that GM is also 1, but we have to find in the case of algebraic multiplicity of eigenvalue 2 is 2. So apply when lambda equals to 1, A minus Ix equals to 0. After solving this homogeneous system, I think I have already told you many times how to solve this system. So what we get, rank is 2 and nullity is 1. So GM should be 1. So in this case, AM is not equal to GM for each eigenvalue, then this matrix A is not diagonalizable. Okay. So if we want to find whether a matrix is diagonalizable or not, we have to just check AM equals to GM for each eigenvalue or not. Result 7. If A square is diagonalizable, then A need not be diagonalizable. Let we have a nilpotent matrix 0, 1, 0, 0. Its A square is 0, 0. It is a diagonal matrix and every diagonal matrix is diagonalizable. But A is not diagonalizable. Its eigenvalues are 0, 0. Here rank is 1 and nullity is also 1. If I am making AMGM table, so lambda here both eigenvalues are 0. Algebraic multiplicity is 1. But A minus lambda x equals to 0. Here lambda is 0. That is Ax equals to 0. That is 0, 1, 0, 0 equals to 0. And what we get? R is 1 and nullity is 2 minus 1 equals to 1. Geometric multiplicity will be 1. So here AM is not equal to GM for eigenvalue 0. So A is not diagonalizable, but A square is diagonalizable. So result 7 says if A square is diagonalizable, then A need not be diagonalizable. Result 8. If A and B are diagonalizable matrices of same order, then A plus B need not be diagonalizable. Let we have a matrix. Let we have a matrix A and B equals to this matrix A is diagonal matrix. Sorry. Upper triangular matrix and its eigenvalues are 0 and 1. And we have discussed if eigenvalues are distinct, then matrix is diagonalizable. So A is diagonalizable. Similar, B is also diagonalizable because its eigenvalues are 1 and 0. But when we apply A plus B, what we get? 1, 1, 0, 1. Its eigenvalues are 1, comma 1. Now we have to find its geometric multiplicity. So 0, 1, 0, 0. Its rank is 1 and nullity is also 1. So AM is 2, but geometric multiplicity is 1. So AM is not equal to GM. So we have find a matrix A and B which both are diagonalizable matrix, but A plus B need not be diagonalizable. These examples help you in find out the counter example in your exams. If you want to discard some options, so you can apply these some results. Similarly, result 9, if A and B are diagonalizable matrices of same order, then AB need not be diagonalizable. Here A is matrix 1 0 and 0 minus 1. It's a diagonal matrix and it is a diagonalizable. B is 1 1 0 minus 1. Its eigenvalues are 1 and minus 1. If eigenvalues are distinct, then matrix is diagonalizable. So A and B both are diagonalizable. But when we find product of AB, one zero zero minus 1 1 1, but this matrix is not diagonalizable because here eigenvalues are 1 1 and 1, but its geometric multiplicity is 1. So the question is, check whether matrix A is diagonalizable over R or over C. In case A is diagonalizable, find a matrix P and D such that P inverse AP equals to D. If matrix is diagonalizable, then we will find a matrix P which satisfies this condition. We have matrix A 1 1 minus 1. We just apply the characteristic equation, formula of characteristic equation of 2 cross 2 matrix, that is lambda square minus में 2 lambda plus 2 equals to 0 and lambda are 1 plus iota and 1 minus iota. We make AMGM table. AM are both algebraic eigenvalues. Algebraic multiplicity with both eigenvalues are 1 and 1. So geometric multiplicity will also be 1 and 1. So A is diagonalizable over C, but not over R, because we will not be able to find a basis in R. So that's why we are saying A is diagonalizable over C but not on R. Now you also know how to find the eigenspace corresponding to the eigenvalue 1 plus iota. By solving this homogeneous system, we get eigenvector 1 iota. Similarly, corresponding to the lambda 1 minus iota, we find eigenvector x2. Okay. Now the task is how to make a matrix P which satisfy P inverse AP equals to D. We have discussed P is made by P can be made by taking eigenvector as columns 1 minus iota. Okay. So here we made a P by these eigenvectors by taking these eigenvectors as column vectors and find P inverse. So P inverse, just you know how to find the inverse in 2 cross 2 matrix. Just change this minus iota and 1 and taking negative of these elements minus 1 minus iota and by divide the determinant. So in this way we find out how P inverse, that is minus iota minus 1 minus iota 1 into a minus 1 by me 2 iota. Now we have to find P inverse AP. By applying this product, we found 1 plus iota 0, 1 minus iota. We find a diagonal matrix whose diagonal elements are eigenvalues, because
because
matrix is
matrix is
diagonalizable. Here result 5 says same. A is let A be n cross and diagonalizable matrix and let x1, x2, xn be an Li eigenvectors of A if P is an n cross n matrix formed by taking x1, x2, xn as columns. Then P inverse AP is diagonal matrix in which elements of the diagonal are the eigenvalues of A. So the matrix is diagonalizable. So we are able to find a matrix P. When we apply P inverse AP, then we get a diagonal matrix whose diagonal entries are the eigenvalues. Okay. Before these questions, we have to discuss properties of eigenvalues. So, eigenvalues of lower triangular, upper triangular, and diagonal matrix are just the diagonal elements. So these are the very simple thing to find the eigenvalues of triangular matrix and diagonal matrix. This is diagonal matrix. Its eigenvalues are A and B. Similarly, upper triangular matrix also, its eigenvalues are A and B. This is very important result. Sum of all eigenvalue of a matrix is equal to its trace. If we have a matrix A, B, C, D and its eigenvalues are lambda 1, lambda 2, then lambda 1 plus lambda 2 equals to A plus D. So sum of eigenvalues is equal to the trace of the matrix. The third result is product of all eigenvalues of a matrix is equal to its determinant. From the above example, if lambda 1, lambda 2 are the eigenvalues and its determinant of matrix is AD minus BC, then product of the eigenvalues is equal to the determinant of the matrix. Lambda 1, lambda 2 equals to AD minus BC. These both results are very important. So please keep it remember. The fourth is all eigenvalues of a non-singular matrix are non-zero. If matrix is non-singular, then its all eigenvalue should be non-zero. Okay. At least if a matrix is singular matrix, then there at least one eigenvalue which is 0. If matrix is non-singular, then there should be there should be no zero eigenvalue, But if there is a singular matrix, then at least one eigenvalue should be a 0. If we the sixth result is, if sum of elements of each row or a column of a matrix is k, then k is the eigenvalue of that matrix, like 1 1 1, like 2 2 2 2. Sum of elements of each row is 4, then 4 must be an eigenvalue of this matrix, lambda square minus 4 lambda plus, and it is 4 lambda plus 0, lambda minus 4, then lambda equal to 0 and 4. If sum of element of each row or sum of elements of each column is k, then k is an eigenvalue of that matrix. Example में you may show, you can see 4 is an eigenvalue of this matrix A. Another eigenvalue is 0 because this matrix is singular matrix. So at least singular matrix, at least one eigenvalue should be 0. So eigenvalues here are 0 and 4. The seventh result, eigenvalues of A and A transpose are same. Number of eigenvalues of n cross n matrix is always n. If we have an n cross n matrix, the number of eigenvalue should be n. But here counting multiplicity, not necessary eigenvalue should be distinct. Ninth, if lambda is an eigenvalue of A corresponding to the eigenvector V, then k lambda is an eigenvalue of Ka corresponding to the same eigenvector V. If we have a matrix A and its eigenvalue is lambda, and we are interested in finding out the eigenvalue of Ka, then its eigenvalue will be k lambda. And the main thing is corresponding to the same eigenvector V. There is no change in the eigenvector. Okay. The 10th result is, if A is a matrix and its eigenvalue is lambda, and we have to find k1i plus k2a, then its eigenvalue will be k1. Eigenvalues of I are 1 1 1. So eigenvalue of k1 I plus k2 is k1 plus में k2 lambda. 11th, if A is a matrix and its eigenvalue is lambda, and we are interested in finding out eigenvalues of A raised to power n, A inverse if exists, or adjoint of A, then its eigenvalue, in this case eigenvalue of A raised to power n is lambda raised to power n. In the case of A inverse, eigenvalue will be 1 over lambda. In case adjoint of A, the eigenvalue will be given by determinant A by my lambda. Here, provided the matrix should be non-singular, that's why we can able to divide the determinant by lambda. 12th, if lambda is an eigenvalue of A corresponding to the eigenvector V and fx be an polynomial, then f lambda is an eigenvalue of fa corresponding to the same eigenvector V. It's a general case of this result, 9th. Okay. So fx can be a polynomial. So we have just to find how we find eigenvalues of fa, just putting x equals to lambda, that is f lambda. And similarly, corresponding to the same vector, same eigenvector V, there is no need there is no change in eigenvector. If lambda is eigenvalue of A, then eigenvalue of A conjugate and A transpose conjugate will be lambda conjugate. Okay. This is the result. If lambda is eigenvalue of A and we have to find eigenvalue of A star A or A star A. Please keep this mind. Mod lambda square need not be an eigenvalue of A star A or A into A transpose conjugate. Okay. We just can say eigenvalue of A transpose A or A transpose conjugate are non-negative real number. If A is non-singular, then we can say these eigenvalue will be positive real numbers. But we cannot say its eigenvalues are mod lambda square. These are the results. Eigenvalues of diagonal matrix is just the diagonal elements. Similarly, eigenvalues of lower or upper triangular matrix are the just diagonal elements. If we what are the eigenvalues of super lower or super upper triangular matrix are 0. Super lower, super upper triangular, it means these type of matrix. Okay. So its all eigenvalues are 0. Eigenvalues of backward diagonal matrices are these types 0 0 d1 0 0 d2 dn 0 0. If n is even, then eigenvalue will be plus minus product of first and last d1 dn plus minus under root of d1 dn. Similarly d2 and dn minus 1. So plus minus under root d2 dn minus 1. If n is odd, the middle one will be same dn plus 1 by 2 and the other eigenvalue will be find out by the same way as in above. Okay. You can clearly understand by the examples. Let we have a matrix A 0 0 2. These are the backward diagonal matrix and here n is even, that is n is 4 and its eigenvalues would be plus minus 8 into 2 under root plus minus 9 into 3 under root, that is plus minus 4 plus minus okay 3 root 3. Similarly, A is here n is odd, that is 3. So plus minus 9 into 4 under root and 5 as it is. Plus minus 6 and 5. So in this way we can find out the eigenvalues of backward diagonal matrices. Eigenvalues of backward scalar matrices are just in this case all backward diagonal elements are k. So in the similar way we can find the eigenvalues of backward scalar matrix as the backward diagonal matrix. Like example 0 0 1, this is the backward scalar matrix, so its eigenvalue will be plus minus 1 and plus minus 1, and in this case plus minus 4 and 4 as it is, and product of this plus minus under root. So the question is find eigenvalues of given matrix. If we observe, this matrix is sum of zero, zero, 4, that is 3i plus m. Okay. Its eigenvalues are plus minus 4 and 4, and its eigenvalues are 3, 3, 3. So what we get at these corresponding eigenvalues, that is 7, 7, and 3 minus 4, that is minus 1. So these are the special type of matrix which is a linear combination of a identity and a backward scalar matrix. Okay, so just make this combination and find the eigenvalues of this and add the corresponding eigenvalues. So these their eigenvalues are 7, 7, and minus 1. If matrix is nilpotent, its eigenvalues are 0. Zero matrix is the only nilpotent matrix which is diagonalizable. You have shown many examples of nilpotent matrix. This matrix is nilpotent and this is a non-zero nilpotent matrix, and their eigenvalues are 0 and 0, and this is not diagonalizable matrix. Only zero matrix is the only matrix which is only nilpotent matrix which is diagonalizable. These are the table. This is the table of eigenvalues and diagonalizability. If we have a real symmetric matrix, then its eigenvalues will be real and it is diagonalizable over R. Hermitian matrix, eigenvalues of Hermitian matrix are always real, but this is diagonalizable over C. Real skew-symmetric matrix, its eigenvalues are 0 or purely imaginary, and it's diagonalizable over C. Similarly, skew-Hermitian matrix, its eigenvalues are 0 and purely imaginary, and it is diagonalizable over C. If we have a real orthogonal matrix, its eigenvalues will be of modulus unity, and it is diagonalizable over C. Unitary matrix, it's also eigenvalues of modulus unity, and it's diagonalizable over C. Idempotent, these are type matrix are of idempotent matrix, and its eigenvalues are 0 or 1, and it is diagonalizable over R. Involuntary matrix is if A square its eigenvalue is -1 or 1. Idempotent and involuntary matrix, and it is diagonalizable over R. Eigenvalues of nilpotent matrix are 0, that is not diagonalizable. That is generally not diagonalizable. Only 0 matrix is diagonalizable. Now, on the basis of these properties, we will do these questions. We have given a matrix A, that is 4, 1, -1, 2, 5, -2, and 1, 1, 2. Now we have to find the eigenvalues of A inverse, A square, A cube, A transpose, and adjoint of A. Lambda square minus 11 lambda square plus 12 plus 11 minus determinant, wait a minute, that is 4 by solving this characteristic equation, we get lambda equals to 3, 3, and 5. So these are the eigenvalues of this matrix A. Now we have to find eigenvalue of A inverse. Yes, we can find eigenvalue of A inverse because it is a non-singular matrix. So eigenvalues of A inverse will be 1 by 3, 1 by 3, and 1 by 5. Eigenvalue of A square is given by just square these eigenvalues. So A square, eigenvalue of A square will be 9,
9,
9,
9, and 1.
20, 25. Okay. Similarly,
Okay, ma'am.
we can find the eigenvalues of A raised to power 3. Just cubing these eigenvalues, we can find the eigenvalue of A raised to power 3. A eigenvalue of A transpose will be same as of eigenvalue of A, that is 3, 3, and 5. Eigenvalue of adjoint A is given by determinant of A by me lambda, that is determinant is 45 by determinant is can be found by just product of the eigenvalue is equal to the determinant of matrix. So determinant is 45 and lambda is 3, 45 by 3 and 45 by 5, 15, 15, and 9. So these are the eigenvalue of adjoint A. Okay. So just find out just finding the eigenvalues of A, we can find the eigenvalues of A inverse, A square, A cube, A transpose, and adjoint A. Now the second question is, if eigenvalue of 3 cross 3 matrix are -7, 8, 9, then find the value of X in matrix. So eigenvalues are 7, 8, and 9. Now we have to find the value of X in matrix. Here X. So we just know the sum of eigenvalues equals to the trace of the matrix. So 9 X equals to 1. Okay. Find the eigenvalues of the following matrix. we have a matrix whose all entries are 1. So by just not doing the calculation work, we can just easily find out the eigenvalue of this matrix. Sum of each row is 3. So 3 must be an eigenvalue of this matrix. One eigenvalue must be 3. Now you can observe rank of this is a singular matrix also, and rank of this matrix is 1. So at least 2 eigenvalue should be 0. If a matrix, if A is a matrix whose rank is R, then at least n minus R eigenvalues are 0. This is the result which we have applied here. So here the rank is 1, so at least 2 eigenvalues are 0. So eigenvalues of this matrix will be 3, 0 and 0. Okay, singular matrix है, its determinant, its product of eigenvalue, that is 0, and sum of eigenvalues equals to the trace, that is 3 plus 0 0 equals to trace of the matrix, that is equals to 3. Similarly, if we have to find the eigenvalue of this matrix, here the eigenvalue will be 4 0 0. Okay, the question is, consider the matrix A, that is 1 1 0 1. Find the eigenvalues and eigenvectors of A and A transpose. Eigenvalue will be triangular matrix. This is a triangular matrix, so eigenvalue will be 1 and 1. You can also clearly see this is not a diagonalizable matrix. Okay, eigenvalues of A transpose also 1 and 1, but the what will be the eigenvectors of A and A dash, that is 0 1 0 0. Eigenvector of will be 1 and 0. Okay, by solving this homogeneous system we get eigenvector even 1 0. Now I am taking A transpose, that is 1 1 0 1. Eigenvalue will be 1 and 1. Now now we will find eigen vectors, that is A minus lambda I x equals to 0. Lambda here is 1, so 0 0 1 and 0. So solving this, A should be 0 and B is free variable. So eigenvector of A transpose will be 0 1. So observe this, eigenvalues of A and A transpose are same, but eigenvector need not be same. E1 and E2 are not same, so eigenvector of A and A transpose need not be same. I hope you have idea how to apply the properties of the eigenvalues. Now the topic is characteristic and minimal polynomial. Now we must know about the annihilating polynomial of a matrix. A polynomial fx is said to be an annihilating polynomial of a matrix A if f of A equals to 0. Minimal polynomial of a linear operator matrix. The minimal polynomial mx of a linear operator T is defined to be a monic. It should be a monic of lowest degree and in of which T is root. That is, if mx is a polynomial, then it should be a monic and should be a lowest degree, and but satisfy, it should be a annihilating polynomial, that is m of a equals to 0. When we put matrix A in the polynomial, then we get 0 matrix. Okay. So this is a definition of minimal polynomial of a linear operator over a matrix. This is the important theorem, Cayley-Hamilton theorem. What it says, every square matrix satisfy its characteristic polynomial. It means if Cx is a characteristic polynomial, then C of A should be 0. When we put A in the characteristic polynomial, then we get 0 matrix. Minimal polynomial is unique. Let Mx and Cx denotes the minimal and characteristic polynomial of a matrix respectively, then Mx and Cx have same distinct linear factor. Like we have Cx x minus alpha beta 1, x minus alpha 1 alpha 2 beta 2, x minus alpha r beta r. Then mx also have same linear factor, that is x minus alpha 1, x minus alpha 2 and x minus alpha r, but power may be different, like alpha gamma 1, gamma 2 and gamma r, and gamma i's will lie between 1 and less than equal to beta I. Okay, so here the linear factor just linear factor distinct linear factor will be same in mx and cx. Power may be of different. The third is a matrix is diagonalizable if and only if its minimal polynomial has no repeated linear factor. We can also check whether a matrix is diagonalizable or not by the minimal polynomial. If minimal polynomial has no repeated linear factor, then matrix will be diagonalizable. You may have an idea from this example. Find the characteristic polynomial and minimal polynomial of this matrix A. So characteristic polynomial you can easily find out because we have already discussed this characteristic equation many times. Now see, characteristic equation is Cx lambda minus 2 square into lambda minus 8. Now minimal polynomial always mx always divide Cx. So possibility of minimal polynomial of A is either lambda minus 2 or lambda minus 8. I have already told you linear factor will be same. Power may be different. Wait. So the possibility of minimal polynomial of A is either lambda minus 2 into lambda minus 8 or lambda minus 2 square into lambda minus 8. So first we will check this polynomial whether it is a satisfy m of when we put a equals to 0, because minimal polynomial should be monic of lowest degree. So we will start from this polynomial, and and it satisfies this condition. So we just put matrix A in this polynomial, and after squaring and uh, do this plus and subtraction, we get 0 matrix. So mx lambda minus 2 lambda minus 8 will be minimal polynomial. If this is not equal to 0, if in some case if this is not equal to 0, then this will be the minimal polynomial, which is equal to the characteristic polynomial. There are some questions. Find the eigenvalues of the matrix. Now you can see this is the matrix of order 6 by 6. So it is very tedious work to do A minus lambda I to find the characteristic equation. So just we have to observe the matrix. So first thing we are observing, sum of each row is 1. Okay. The second thing is this is the symmetric matrix. Aij equals to Aji for all I and j. So this is symmetric matrix. Now eigenvalues of symmetric matrix are of always real. Now we are observing this is also an orthogonal matrix. Orthogonal matrix is A into A transpose equals to identity, or we can say this is the permutation matrix. So eigenvalues of orthogonal matrix is whose modulus is unity, but all eigenvalues should be real, because this is this matrix is also symmetric matrix. So what are the possibility of lambda? Only plus and minus 1. And now the problem, how many times 1 and minus 1? So we will see here the trace is 0. So we can say 3 times 1 1 1 and 3 times minus 1 minus 1. So in this way we can find the eigenvalue of this matrix. Just observe the matrix and find the possibilities. The next question is, find the characteristic polynomial, minimal polynomial and determinant of the given matrix. So this is also an matrix of high order. So what we are observing here, just make a block matrix. Okay. We make a block matrix and it becomes a block diagonal matrix. Now we have to find characteristic polynomial, minimal polynomial or determinant. So these are the results of block diagonal matrix or block triangular matrix. If we want to find the characteristic polynomial of a whole matrix, so we just have to find the characteristic polynomial of each blocks, and product of these characteristic polynomial gives the characteristic polynomial of the whole matrix. Similarly, minimal polynomial of whole matrix is equal to the LCM of m1 M1x, M2x and M are x. And determinant of A is given equals to determinant of product of determinant of each block. So here we will find characteristic minimal and determinant of this matrix. We have just made out the block of this matrix. So this is one block, this is second, and this is the third. The C1x characteristic polynomial of the first block is x minus 2 square, and C2 C2x is x square minus 9x plus 14, and C3x is x minus 7. Just find the characteristic polynomial of each block. Now Cx characteristic polynomial of A is given by C1x into C2x into C3x. Okay. Now we have to find minimal polynomial. So this block matrix is not diagonalizable. So minimal polynomial will be x minus 2 square, m1x, m2x. Its eigenvalues are x square minus 9x plus 14, that is 7 and 2. The x minus 2 and x minus 7, and m3x equals to x minus 7. Now we have to find minimal polynomial of the whole matrix A, that is by taking LCM of these m1, m2 and m3x, that is x minus 2 square and x minus 7. Okay. And now we have to find determinant of A. Determinant of this block is 4. That is 14. Second determinant of second block, and third is 7. Just multiply this 4 into 14 into 7, we get the determinant of A. The next question is the distinct eigenvalue of the matrix will be, see, this matrix is singular matrix and its rank is 1. At least 2 eigenvalue will be 0. Now the third eigenvalue can be decided by decided by the trace. So lambda 1, lambda 2 plus lambda 3 will be equal to 2, and we have already observed 2 eigenvalues are 0. So the third eigenvalue will be 2. The distinct eigenvalue of this matrix will be 0 and 2. This is an this question was asked in GATE. The question is the minimal polynomial of the matrix. We have this matrix. You can make this matrix into block diagonal matrix. So m1x will be x minus 6 and x. See, sum of each row is 6 and rank is 1. So one eigenvalue will be 0. So m1x will be x minus 6 into x, and m2x will be x minus 6. Now just by taking LCM, we get the minimum polynomial of the matrix, that is x into x minus 6. Okay, the fourth option is correct. The next question is, which of the following matrices is not diagonalizable over R? We have to find which is not diagonalizable over R. So when we see second and the fourth option, eigenvalues are 1, 2 and 3. All eigenvalues are distinct. It means matrix is diagonalizable. Similarly, in the fourth option, eigenvalues are 1, 2 and 3. It is also diagonalizable. So second and fourth options are not correct. Now we have to, now the eigenvalues of first is 1, 1 and 2. It means its GM is 1 because its algebraic multiplicity is 1. But the question, but here we have to check what will be the geometric multiplicity of the eigenvalue 1. So we just check 1 minus 1 0 1 0, 0 2 minus 1 1 0 0 0 and 0. Rank is 1 and algebraic multiplicity is n minus r is 2. So here am is equal to gm for each eigenvalue. So this is also a diagonalizable. So this is also a wrong. So option third will be correct. Or you can check by find out the geometric multiplicity of corresponding to the eigenvalue 1, that is 1 minus 1 0 1 0, because here eigenvalues are 1 1 and 2. So we have just checked the geometric multiplicity of eigenvalues 1 0 0 0 0 0 1. Rank is 2 and n minus r is 1. So geometric multiplicity is 1. But algebraic multiplicity of this matrix is 2. So this is not a diagonalizable matrix over R. Now the next question is, if A is 2 cross 2 matrix over R with determinant of A plus I equals to 1 plus determinant A, then we can conclude that. So if A is 2 cross 2 matrix over R, let us suppose eigenvalues of A will be lambda 1 and lambda 2. Okay. Determinant of A is product of eigenvalues. So we can write here 1 plus lambda 1 lambda 2 equals to. Now eigenvalues of A is lambda 1 and lambda 2, and eigenvalue of I is 1 and 1. So eigenvalues of A plus I will be 1 plus lambda 1 and 1 plus lambda 2, and its determinant can be given by the product of these eigenvalues. So 1 plus lambda 1 into 1 plus lambda 2. Now just solve this. 1 plus lambda 1 lambda 2 equals to 1 plus lambda 1 plus lambda 2 plus lambda 1 lambda 2. So lambda 1 plus lambda 2 equals to 0. Sum of eigenvalues equal to the trace of matrix. So we can conclude that trace of A should be 0. So third option will be correct. The next question is, let M be an n cross n and n is greater than equal to 2 non-zero real matrix with m square equals to 0, and let alpha is non-zero real number. then these are the options. So what we have given, M is non-zero real matrix, but M square equals to 0. It means M is nilpotent matrix. Okay. And eigenvalues of nilpotent matrix are 0, 0, n times if matrix M is M is n cross n order matrix. So now we have to find the eigenvalue of M plus alpha I and M minus alpha I. So eigenvalues of M are 0 and eigenvalues of alpha is alpha. So in this case, all eigenvalue will be alpha, but in this case, all eigenvalue will be minus alpha. So what A option says, alpha is the only eigenvalue of M plus alpha I and M minus alpha I. But here the eigenvalues are alpha and minus alpha. So option A is wrong. Similarly, alpha is the only eigenvalue. Its eigenvalue will be alpha and its eigenvalue will be alpha minus 0, that is alpha. So alpha is the only eigenvalue of M plus alpha I and alpha I minus I. Yes, this is correct. Let A be a matrix. Now we have to find the largest eigenvalue of A. Okay. So observe this matrix. What we see, 4. Sum of each row is 4. So one eigenvalue will be 4. And the you can see these two rows are the same. So rank is less than 3. That is, it is a singular matrix. At least one eigenvalue will be 0. Okay. Now 4 plus 0 plus lambda 3 equals to a trace of the matrix, that is 2 minus 2, that 0. So lambda 3 will be minus 4. So we have eigenvalue of this matrix will be 4, minus 4 and 0. Now we have to find the largest eigenvalue, that will be 4. The next question, let M be a matrix, then the value of determinant 8I minus M cube. So how to find this? Just take 8I minus M. 80008000080 and minus M 9271. After subtracting this, we get minus 1, minus 2, minus 7, minus 1, 0, 1, minus 2, minus 1, 0, 0, 8 minus 3, 11, and minus 6. The next is 0, 0, 5, and 8. Okay. You can find out the eigenvalue by making this as block diagonal. Its eigenvalues are minus 1 and 1. Its eigenvalue will be x square minus 5x plus plus 6, that is 2 or 3. So its eigenvalue will be minus 1, 1, 2 and 3. This is the eigenvalue of 8I minus M. Now we have to find 8I minus M eigenvalue of 8I minus M cube. So just cube of these eigenvalue, that is -1, 1, 8, 27, and product of these eigenvalue give the answer of determinant. Okay. The next question is, let M be a real 6 cross 6 matrix. Let 2 and -1 be two eigenvalues of M. If m raised to power 5 equals to AI plus BM, where A, B belongs to R. So here, these are the eigenvalues. And you have to find the values of A and B. So these eigenvalue must satisfy this equation. So just put these value in this equation and you get the answer of A and B. I think we have short of time, so I'm just giving you an idea how to solve these questions. The next question is the number of linearly independent eigenvector of the matrix. Similar, we can make this matrix into block diagonal matrix and find the eigenvalues of this block and this block, like 3x plus 2 minus 4, that is -2, and its eigenvalue will be x square minus 7x plus 12. I think it will have two distinct eigenvalue, and it also have distinct eigenvalue 4 and 3. So for each distinct eigenvalue, there will be their corresponding eigenvector will be linearly independent eigenvector. So the answer will be 4. The next question, let A be 3 cross 3 matrix with eigenvalues 1, -1, 0, then the determinant of I plus A 100. So just find the A raised to power, eigenvalue of A raised to power is lambda raised to power n. So just it will become this, and eigenvalue of I is 1, 1, 1. Add the corresponding eigenvalue. What do you got? 2, 2, 2, and 1. And determinant can be found by the taking product of these, that will be 4. So this is all from my side. If you have any query or questions, feel free to ask.
I'm Varada from Mahatma Gandhi College, Iritty.
Hello.
And I found the class extremely well. The topics were very clear, and we're honestly looking forward to receive more classes from you. Thank you, ma'am.
Thank you.
Hello, ma'am. My name is Alina Anna Matthews. I'm currently third year BSc student of Mahatma College, Chungatra, Kerala. Thank you, ma'am, for such a wonderful class. You've explained it so well, a detailed explanation. Can you share the PDF of the notes?
Yeah. I will
Thank you.
forward to the sir. Sir will provide you.
Okay.
Thank you, sir, for organizing such a class. Thank you, ma'am. Thank you, sir.
Thank
Yes,
you.
thank you, Alina. Thank you, Alina.
Aguila.
Hello.
First of all, thank you so much for this nice session. You have discussed so many questions. I really like it. Actually, I really like metrics theory, and I hope all others enjoy this session too.
Yes,
Hi,
Mohsin.
ma'am. My name is Musina. I'm from Southside College, Kannur. First of all, thank you so much for your very helpful class, for your valuable time. As your exams are getting so close, we all have started working so hard, preparing so hard for our exams. So classes like this are very helpful for us. Thank you so much.
Thank you.
Thank you for listening me.
I'm Shikha from, I'm studying in BIT Mishra College from Jharkhand, and I'm in second year I'm a second year mathematics student, MSc mathematics student. Ma'am, your session was really nice. You explained every theorem result in a very detailed manner, and overall the class was very great. And thank you for organizing such sessions. And thank you, sir, for organizing such sessions. And
Thank you.
and today is Chhat Puja, so I would like to wish everyone happy Chhat Puja.
Happy Chhat Puja to all of you. Yes, sir. This is the beauty of this session because it
Yeah.
connected all over the India.
Jiva Priya, and I'm from Puducherry. 2022 passed out. I did my MSc just now. So now I'm fully spending my time for CSIR net only. So today I attend your lecture. It's really very helpful to me because within 2 hours I can learn a lot things. So your work is very great here. So thank you so much, ma'am. And can you suggest me any book for linear algebra?
Yeah, there's a lot of linear algebra books. The first, if you want to practice more and more questions, then you can start from the Shom series. And if you want to read the classic books, then you can go for the 𝐤𝐿𝐵, and you can go for David Seeley, or you can also read Fred Burke. So
Okay, ma'am.
just decide which book you are easy you can learn, yeah, or understand. So just go through these books. Or if you want to practice more questions, then go for the Shom series.
Oh, okay, ma'am. Thank you so much. And
Okay,
can
thank you.
you share me your what's that clearing JRF experience? How you cleared? Like, can you share anything?
Yeah, just the cut off the net exam or CSIR JRF is based on the number of the easy question you would attempt. Okay, so
Okay, ma'am.
please do not make silly mistakes. If there are easy questions, please do not make any silly mistake. Carefully do those questions, because easy question will decide the merit or cut off the exam. And please go through all subjects, like do not skip any subjects, like do not skip purely or applied part, or so just keep practicing previous year questions. Please take more and more test series. It will be helpful for you to clear the
Oh,
exam.
okay, ma'am. Ma'am, I'm very bad
Okay.
in part A, quantitative section. So this part, how can I study, ma'am? Can you give any tips for that?
There is a book, R.S. Agarwal, for the quant part, so you can go for that book,
Okay,
R.S.
ma'am.
Agarwal.
Jivapriya, we had one session on Part A, how to crack Part A
Okay, ma'am.
by Sushmita
Sir.
but it was there in our YouTube channel. You can watch it. It's a very good session on cracking the Part A questions, how to attend that, and
informative, and you have included a lot of questions. I think it will be very informative for our preparation for JAM examination. So thank you, ma'am. Thank you so much. And thank you, Vinod, sir. Thank you so much.
For making the session as beautiful. I have learned many things from the session, even though I know about the eigenvalue, but I have learned more in today's session. Thank you, ma'am. Thank you, sir, for organizing a wonderful session. How to crack a section B without any mistake. I was very poor in section B part in JAM.
Actually, I have no
Oh.
idea about the IIT JAM that much.
Binny, she is asking about multi-selected questions.
Hi.
Oh, okay,
See,
yeah.
for JAM examination, there are 3 types of questions. One is multiple choice, another one is multi-select type, and another one is numerical answer type. These are the 3 different types.
Yes. Multiple select. In multiple select question, please carefully read each and every options. Okay.
Okay, ma'am.
If there is a option for which you can take proof or find the proof, so it will be good. Otherwise, go for the counter examples, because it will help you to discard the options. So this is the main concept in multiple select questions.
Okay, ma'am. Thank you, ma'am.
Okay, thank
Yes,
My
Sarah.
name is Rahmalta, and I'm from Tirur, TMG College. And first of all, thank you, ma'am, for this wonderful section. It's very helpful me, and I hope other students also enjoyed this session. And you explained all theory and topics very clearly. And we are expecting more session like this. And thank you, sir, for conducting this section. Thank you, ma'am. Once again, thank you.
Thank you.
Ma'am, I'm Tithi Biswas. I am a second year student. Ma'am, today's session was very helpful for us, as you covered the whole topic, and along with the questions and the concepts. Ma'am, I wanted to ask something related to the previous question. As you know, in NET exam there was part C that has also multiple select question, and sometimes I feel that it is difficult to correct all the options. And so can you suggest something that how you prepare for part C, or how you attempt in the exam during your NET exam?
Okay, the first thing is sometimes there will be a question which is basically depend upon the theorems, statement of theorems. Okay, so you just have to read books carefully. Okay, the more you read, the more you get about the concept. Okay, the second thing is try more and more questions. Please take lots of test series, do lots of tests, lots of previous year questions, so it will help you to decide or to help to discard the options. I think this is the major thing to uh, attempt the multi-select questions.
Okay, ma'am. Thank you so much for your suggestion, ma'am.
Yeah,
Thank you.
Thank you, Titi. A strong conceptual background along with a good practice of problems. That is the success mantra for any competitive examination for this kind.
Hello, ma'am. I'm Malvika, third year BSc Maths from the 𝐤𝐢𝐭𝐡 College, Kozhikode. Thank you, ma'am, for this wonderful session. It is really helpful for us. Thank you so much for helping us. We are expecting more classes from you. Thank you so much for your effort and time. I would also like to thank Vinod sir for conducting such a wonderful session for us. Thank you, sir and ma'am.
Thank you.
Thank you, Malavika. Yes, Shilpa.
Good afternoon, ma'am. Good afternoon, sir. Thank you, ma'am, for conducting such a wonderful session for us. It was a really wonderful one, and eigenvectors and eigenvalues are one of my favorite topics. So even though I faced a power supply problem, then also I managed to attend the class because I love this topic. Thank you, ma'am, and thank you, sir. Looking forward for more classes from you, ma'am. Thank you, sir.
Thank you.
Thank you, Shilpa. Yeah, this.
Ma'am,
Yes.
ma'am, I am Anamika from Kerala. Thank you, ma'am, for this session. And I have a doubt, ma'am. Can I ask?
Yeah, you can ask.
You told that, ma'am, when the sum of the rows are equal, we can the one of the eigenvalue will be that number. If even the numbers arranged are different, like please consider a matrix like 2, 3, 5, 6, 3, 1, 7, 3, 0. These numbers are different, but the sum are same. So can
Yes.
we?
Yes. That will be an eigenvalue.
Oh, that's thank you, ma'am.
There's a no
Thank
need
you.
an element should be same. The sum of each row or sum of each column should be same. Then the sum will be an eigenvalue.
Ma'am, that's why I'm asking. Even the numbers are different.
Yes, if we are saying 1 plus 2 plus 3, that is 6. The next row has 0, 6, 0. It also a 6. Then 6 will be an eigenvalue of that matrix.
Okay, ma'am.
Okay. Thank you.
So once again, Binny, thank you very much for being with us and for this wonderful session. And I hope that you will be again come for one more session with more problems from the area of linear algebra, possibly before the JAM examination. And I would like to express my thanks on behalf of Math Aspirants Group. Also, I would like to wish you all the success in your academic career and research. All the very best. Thank you, Binny. Thank you, everyone. Let us
Thank
wind
you,
up.
sir. Thank you, sir, for giving me this opportunity. And I like this session. And I will I will continue with you in future also. Thank you for listening me and patiently listening me. So thank you so much.
Thank you. Thank you, Binny. Let us wind up here. Thank you. Thank you,
Okay,
everyone.
sir. Bye, sir.